Thank you for joining us today for our webinar on Understanding Laboratory Standards. My name is Nicole Olson, and I will be moderating today's event. This presentation is copyrighted by Price Industries. Before we begin, I would like to go over some administrative items. This webinar is being brought to you by ANSI Controls and is accredited for 1 professional development hour. After the event, all those who have signed in will receive an email with a link to request your PDH credits for attending the webinar. Questions can be submitted anytime during today's presentation using the chat or question function on your toolbar. We will try to answer all of your questions during the Q&A session at the conclusion of the presentation. Audio is being broadcasted through the internet. However, if you experience any audio problems, please call in using a phone line and the phone number provided for you on the toolbar. And now to introduce you to today's presenter, Michael Lepke. Michael is a mechanical engineer with over 6 years of experience with critical control systems. He oversees the ANSI Controls field support team and uses his vast knowledge of the products to support technicians through product installation and troubleshooting. Michael develops and delivers ANSI Controls technician and advanced technician training classes. Today's course description is: when designing a laboratory, it is important to consider many different factors in the ventilation system and how they may affect the overall design of the laboratory. Understanding the standards that provide guidance on how to design around these factors is important to ensure the system is safe and efficient. In this webinar, participants will learn differences and similarities between laboratory ventilation standards, ASHRAE Laboratory Design Guide, ANSI Z9.5, NFPA 45, ASHRAE 110, a Canadian-specific standard, CSA Xiii16.5, and NEB. In addition, you will learn typical range for the air change rate in laboratories, the effect of diffuser and fume hood placement on fume hood performance, how best to implement fume hood diversity into the design of the laboratory, typical pressurization of laboratory spaces and how to define it in the design process, and the basics of fume hood testing procedures. I will now pass the presentation over to Michael.
Thank you, Nicole. So today we're going to start off by talking about the types of laboratories and equipment that you may see and what standards apply to each of those types of rooms and equipment. We'll then talk about the air change requirements that are required and recommended from the standards in laboratories. We'll talk about the speed of response and how that's defined in the standards, as well as air distribution and recommendations for laying out diffuser and fume hood placement. We'll also talk about room pressurization in laboratories and how the standards call that out, as well as fume hood diversity and doing an example of how to lay out fume hood diversity and implement it. The last thing that we'll discuss today is test methods for fume hoods and the standards that go along with that. So if we start first with the types of laboratories and equipment that we may see, what we'll be going through here is definitions that come from the ASHRAE Laboratory Design Guide, outlining different types of laboratories. So in this section, we'll explore 2 different types or categories of rooms, one being biological laboratories and the other being chemical laboratories. Within those, we'll have different types of rooms, but we'll explore what the standards, which standards apply to those different spaces. We'll also go through different types of equipment exhausts that are used in laboratories along with the standards that apply to those. So if we start by going through biological laboratories, the first room that we'll discuss here is an animal laboratory, also referred to as a vivarium. Now, the purpose of these spaces is to maintain clean and humane conditions for animals, while also providing safe separation of these animals from the lab personnel. Vivariums are not included in the scope of ANSI Z9.5. The second type of room that we'll discuss here is biological containment laboratories. These are laboratories working with infectious agents, and they're characterized here by BSL 1 through BSL 4. If we start by going through the least hazardous at the bottom of the pyramid here, BSL 1 are considered labs that are not, or that have pathogens that are not known to consistently cause disease in healthy adult humans, and pose minimal potential hazard to the lab personnel. BSL-2 here is rated as moderate potential hazard to personnel and the environment, and we may cause mild infection to humans with the infectious agents that they're using in the lab. So these two here are highlighted green as they are included in the scope of ANSI Z9.5. However, as we start going up the chart in hazard level here, BSL-3 would be considered anything that has microbes that are either indigenous or exotic, and they can cause serious or potential lethal disease through respiratory transmission. And the most serious that we have is BSL-4, in which we're using dangerous and exotic infectious agents posing a high risk of aerosol transmitted infection. And these ones are frequently fatal, and treatment or vaccines are not available for these diseases. These ones here at the top of the pyramid, BSL-3 and 4, are excluded from the scope of ANSI Z9.5. Just as a note about BSL-4 labs as well, these are not common labs. There are only about 50 of these BSL-4 labs throughout the entire world. So our next type of room that we'll discuss here again falls into the biological laboratory category, but is a hospital or clinical laboratory where they provide chemical or biological testing of specimens associated with patient care. So typically nothing too hazardous. These ones are included in the scope of ANSI Z9.5 and NFPA 45. So moving on to our next category of room, we'll talk about chemical laboratories, the first of which is a synthesis lab. These are used for organic or inorganic reactions for a wide variety of chemicals, and they're generally not used with hazardous or potent chemicals in large quantities. These would be your general purpose labs. And these ones are included in the scope of ANSI Z9.5 and also NFPA 45. The next type of space that we have in the chemical laboratories is considered a teaching lab. Now these ones are similar to synthesis labs in application, but they are requiring accommodation for large groups and also open line of sight for instructors to see equipment to prevent potential hazard. So these might be large rooms with 20 fume hoods around the exterior of the room, or they may be fume hoods in the center of the room, but with glass sides so that the instructor can see through everything. Teaching labs are included in the scope of ANSI Z9.5 and NFPA 45. The next type of lab here is an explosives lab. So they are similar to synthesis labs in design, however, they do require extra consideration for compounds that may cause combustion or explosions. Explosive labs are not included in the scope of ANSI Z9.5 or in NFPA 45. Our next type of lab is a radiochemistry lab. Again, they are similar to synthesis labs in design, but they require extra consideration for radioactive chemicals. These as well are excluded from the scope of ANSI Z9.5 and NFPA 45. So moving on to the types of equipment that we'll see in spaces. The first one that we'll see here is a fume hood, where we're maintaining inward airflow to the opening of a hood containing airborne materials created during chemical experiments. So when we're mixing chemicals that could create fumes, that will be done inside a fume hood. These ones here today, we're going to discuss the following 4 standards. They're all included in, our fume hoods are all included in their scope, which is ANSI Z9.5, ASHRAE 110, as Nicole mentioned, a Canadian standard called CSA Xiii16.5, and then the NEB procedure for testing fume hoods. The second piece of equipment that we may run into in laboratories are biological safety cabinets. These ones will be used in biological labs for maintaining inward airflow to prevent the release of the toxic particulates and infectious biological aerosols. These ones, biological safety cabinets, are excluded from the scope of ANSI Z9.5 and also CSA Xiii16.5. So our next topic will be air change requirements. Air changes per hour in a laboratory are important to ensure that any potential airborne hazard is properly diluted and exhausted. We'll go through the following standards that cover the typical recommendations for air changes that would be required in a laboratory. The first one that we'll talk about is the ASHRAE Laboratory Design Guide. Here we have our first part of the sentence here is fixed minimum airflow rates in the range of 6 to 12 air changes per hour when the space is occupied have been used in the past. So 6 to 12 is a pretty typical range for the amount of air changes that we need in the space. However, recent universities' research has showed that a significant increase in the dilution and clearing performance when we increase the ventilation rate from 6 to 8 air changes per hour. And as we get above 12 air changes per hour, we start to see that dilution and clearing performance trail off. So this indicates that minimum ventilation rates at the lower end of the 6 to 12 air changes per hour may not be appropriate for all laboratories. It then goes on to state that minimum ventilation rates should be established on a room-by-room basis, considering the hazard level of the materials expected to be used in the room and the operations and procedures that are to be performed. So as the hazard level, materials and use of the room change, an increase or a decrease in the minimum ventilation rate should be reevaluated. So if you're using harsher chemicals in a space and you require more dilution, then we would recommend, or the standard would recommend evaluating that and potentially increasing the amount of air change rates for the hazard that's being used in the room. ANSI Z9.5 also states something similar, that an air exchange rate cannot be specified that will meet all conditions. Excessive airflow with no demonstrable safety benefit other than meeting an arbitrary air change rate can waste considerable energy. So when designing a building with multiple labs, we'll want to make sure that we don't provide just one standard air change rate for all of the labs, as there might be labs that need 12 air changes per hour for the hazard in the space, but to apply 12 air changes per hour in all of the labs might be an energy or might waste energy, and we might be able to reduce the amount of air changes per hour in some of the less hazardous spaces. NFPA 45 here states that a minimum ventilation rate for unoccupied laboratories is 4 air changes per hour, where occupied laboratories typically operate at rates of greater than 8 room air changes per hour, consistent with the conditions of use for the laboratory. So again, we'll make sure that we're designing the room for any of these standards for the hazard that's in the room. And typically what we see is a recommended range of somewhere in the range of 6 to 12 air changes per hour. However, there are cases where the room itself may warrant more than that. These are generally special cases for specific applications, but they should still be considered when designing laboratories. Our next topic is speed of response. For speed of response here, we'll discuss how ANSI Z9.5 defines it and some recommendations that they have for the speed of response in the space. So the first thing we'll start off with is the speed of response is defined as the VAV system shall be capable of maintaining the offset flow required between exhaust and supply to achieve the desired area pressurization within the desired time specified. For most operations, 10 seconds will be an acceptable time to achieve the desired area pressurization, but a hazard evaluation should be conducted to determine the acceptable time. So similar to our air change requirements, ANSI Z9.5 here states that while 10 seconds may be acceptable for most areas, a hazard evaluation and understanding what's going to be in the room is important so that it can be defined ahead of time what response time is required for the space. So this is the speed of response that's required for the room should be dictated by the engineer in the project documents. It also states, or ANSI Z9.5 also states that in a laboratory with ordinary construction and a properly functioning ventilation system, air can move briefly in the wrong direction. So as we open doors, room pressurization will not be maintained. And in most cases, it is acceptable for air to briefly move out of the door before we maintain our proper flow direction again when the room stabilizes. If you are designing rooms that require no air to exit the space, then there are special construction techniques in operation that can eliminate that migration. However, they do fall outside of the scope of ANSI Z9.5. Our next topic here is air distribution. In this section, we're going to discuss some of the considerations that must be taken into account when laying out diffuser and fume hood placement in the lab. So reading the ASHRAE design guide, improper placement or selection of a diffuser can result in disturbing the airflow near the hood face and result in the contaminants from the hood exiting back into the room. So what this is saying here is that higher velocity over the face of the sash can actually pull air back out of the fume hood, and understanding where the diffusers in the room are going to be placed can help us eliminate that effect from happening. If diffusers are placed next to or right in front of fume hoods, higher velocity can pass over the face of the sash and make that fume hood less effective at containing the fumes inside of it. If we talk about ANSI Z9.5, the location of laboratory chemical hoods and other vented openings with respect to open windows, doorways, and personnel traffic flow directly influence the containment ability. So even things like open windows and open doors and people walking in front of the fume hoods can actually create enough cross current or enough turbulent airflow in front of the fume hood to decrease the hood's containment ability. So again, when laying out the room, it's important to understand where those fume hoods are going to be placed in relation to all of those things, as well as your supply diffusers. Moving on to the CSA Z316.5 standard. It as well states something very similar in that we want fume hoods to be located out of the normal traffic pattern and away from any interfering room air currents. Again, these can be caused by doorways or general ventilation. The second thing that it does stipulate here in the CSA standard is that we want fume hoods to not be installed face to face with each other with a small distance between them. So if we have two fume hoods in a narrow room that are 3 feet apart, well, that 3 feet, first of all, may not be enough room for two people to work on each of those fume hoods without being directly back to back, which won't be super convenient. The other thing that can happen there is that when the fume hoods are open, they can create turbulent air in front of themselves and actually pull air out of the other fume hood. So we want to be careful with placing fume hoods face to face, making sure that there's enough distance between them and that they're not affecting each other as they're controlling the face velocity. The other thing that CSA highlights in the standard is acceptable ranges of good and poor performance in terms of crossflow. So when laying out fume hoods and diffusers, we want to keep this in mind that good performance on a fume hood in terms of crossflow would be having less than 30% of our face velocity as a cross draft. So if we have a fume hood that has a set point of 100 feet per minute and we have less than 30 feet per minute of cross draft, that means that we should have good performance on that fume hood. As we start to increase the velocity above 30 feet per minute, we start to see that performance degrade and potentially see airflow coming back out of the fume hood. The NFPA standard as well dictates that room air current velocities in the vicinity of the fume hood should be as low as possible, and ideally less than 30% of the face velocity of the fume hood. So again, that 30% of the face velocity is where we want to target, 30% or less. So if we look at a couple examples of rooms that have this potential issue here, the first example that we have is a row of fume hoods exhausting in a teaching lab, and we have a row of supply diffusers as well that are roughly 2 feet away from the sashes or the faces of the fume hoods. So dropping air directly down right here could cause higher velocity air currents in front of the sash, and that could affect the performance of the fume hood itself. In the case of laying out these diffusers here, we may want to add another ceiling tile or two in here to create some space between where the supply air is coming down and where that fume hood's face is. Another example would be from the ASHRAE laboratory design guide. So in this example here, we have an example of 2 fume hoods that may be placed too closely together in a corner. So in this corner here, we're going to be trying to exhaust air out of one fume hood that may be pulling air out of the other fume hood. So creating some separation between those fume hoods may be a good idea so that we don't affect the performance of either hood. The next topic that we'll discuss is room pressurization. So room pressurization is key to ensuring that contaminated air does not pass into a clean space. So in the following standards here, we'll discuss how the use of the lab will dictate the pressurization of the space. So if we first talk about the ASHRAE laboratory design guide, spaces such as clean rooms and tissue culture rooms are typically positively pressurized to prevent unwanted pollutants from entering from the surrounding or adjacent rooms. The clean room will be used and is considered the clean space in this scenario. Therefore, we don't want dirty air from the adjacent room entering the clean room. Most other labs must be negatively pressurized to prevent the airborne pollutants generated in the labs from migrating to other areas of the building. So in the case of a chemical lab where we may be mixing chemicals that are toxic to humans, we want to make sure that that air that's in the dirty space in the lab does not exit and enter the adjacent spaces that would be considered our clean spaces. Now, a typical value for the room pressure differential is 0.05 inches of water gauge. So whether that's negative or positive just depends on the use of the room, but typically room pressure differential could be 0.05. Moving on to ANSI Z9.5. So as a general rule, airflow shall flow from areas of lower hazard to higher hazard. So unless the room is a clean room or an isolation or sterile laboratory, we want the highest hazard in the room to be the highest hazard room to be the most negative in the pressure cascade. So if we have an area that's being used for more general applications and an area that's being used for working with hydrofluoric and nitric acid, we'll want airflow to flow to the general area and then into the more hazardous lab. Now, how do we lay this out on mechanical plans is important. So the way that we'll set this up, or the way that an example of how we can lay this out here, is that if we have a mechanical drawing where we have a lower hazard room on the left here and a higher hazard room with a fume hood in it on the right side of the screen. Now, the lower hazard room may still have something toxic in it, which is why we have negative 200 CFM coming in from the corridor, which is designated by your 200 CFM coming in through this doorway. And then going into our higher hazard room, we can lay out another 100 CFM traveling through this doorway. So this means that as we open doors in here and enter spaces, airflow will flow from the corridor into the lower hazard room and then into the higher hazard room from the lower hazard room. So this can be a useful way of showing this on the mechanical plans. to designate the direction of airflow and the pressurization of each space. The next topic we'll discuss is fume hood diversity. So fume hood diversity can be a great way to save energy and save installation costs, but it is very important that it's implemented correctly. So we'll go through how ANSI Z9.5 describes diversity, as well as the important steps that must be taken to properly implement the concept. So diversity is a system design concept that can justify sizing components for a total load that is less than the sum of the individual peak demands. So essentially what this means is that we'll design a room, if we're designing a room to have a diversity condition, our supply valve will not be able to supply enough air to maintain the room offset if all of our fume hoods in the lab are open. If our room is designed to have full capacity on the supply and keep up with all of the fume hoods, then we would have a 100% diversity scenario. But if we do have that condition where the exhaust sum can exceed the supply air that we have accessible while not maintaining room pressurization, that becomes a scenario where diversity exists. The advantages of using this system are that we can decrease some of our operating costs, as we know that the room won't operate as high of an airflow, and it can save on initial upfront cost as well, because we can undersize or lower the size of some of our components in the space. However, it is important to implement this correctly. So when designing around diversity, the following things need to be considered. There is quite a large list of things here that need to be considered in that process, but to highlight some of the more important ones. First of all, we need to make sure that we're considering our minimum and maximum ventilation rates for each lab. So the components that we're putting in the space still need to be able to maintain our minimum air changes and our maximum air changes for the space. The second thing to consider that's very important is the sash management or the sash habits of the users. So when people are using fume hoods in the lab, when they open a sash and run an experiment, do they close the sash while that experiment is running, or do they typically walk away while it's open? That is an important consideration because it will be important to communicate that to the users. The last one would be use patterns of variable volume fume hoods. So are 100% of the fume hoods being used at any given time, or will there be 50% of the fume hoods used only as a maximum? Some more considerations to take into account with ANSI Z9.5 is that acceptance of all the hood use restrictions by the user groups needs to be obtained. Designers must take into account the common work practices of the site users. So again, what I mentioned before, making sure that we understand and that the designer understands how the room is being used, and that all of the hood use or the users in the space accept how it will be used when it's in diversity. The second one is very important here as well, is that a training plan must be in place for all the laboratory users to make them aware of any limitations imposed on their freedom to use the hoods at any time. So if we do have a condition where we can only use 50% of the hoods in the lab at any given time, then we do need to make sure that there's a training plan in place for anybody who will be in the room to make sure that they don't open 75 or 100% of the fume hoods. The third thing here is that we need to implement an airflow alarm system to warn users when we may be operating in the diversity condition. And they need to understand what that means so that they can react accordingly. The last thing would be that we need to understand if there will be any restrictions on future expansion. So ANSI Z9.5 talks about fume hood diversity. Our ASHRAE 110 standard also talks about diversity in a slightly different manner, in that it talks about it in terms of maximum allowable sash height. So building ventilation systems may be designed to keep up and maintain sufficient face velocity through a reduced opening, meaning that we wouldn't be able to maintain face velocity if the sash is at the full open position. Once the laboratory hood is past the design opening, hood performance may degrade in these scenarios. So we want to make sure that we impose and train our users to have administrative control and have a system in place to understand those limits and work within those limits. So if we go through an example of fume hood diversity here, what we have on screen is a sample room essentially where we're trying to maintain a 100 CFM room offset target at all times. Now our supply has a range of 90 to 1500 CFM, and when that room is occupied, we're going to try to maintain that room at 1100 CFM at all times. So that's indicated here on the left side of the screen. We can see our room offset of negative 100 and our total supply airflow of 1100 CFM. Now to maintain that room offset, our total exhaust needs to be 1200 CFM. And to achieve that, we have a general exhaust valve that has a range of 90 to 1500 CFM, so the same as the supply. We also have one fume hood in the space, which has a minimum CFM of 100, and when the sash is open, we'll be controlling to 600 CFM on the fume hood. So in our closed position right now, we have 100 CFM being exhausted from the fume hood. Our general exhaust is controlling to 1100 CFM to maintain our total exhaust and our room offset. So when we open the fume hood here, we're going to see that the fume hood exhaust increases to our maximum CFM, which is 600. Our general exhaust then adjusts down to 600 CFM to ensure that we maintain that total exhaust of 1200, ultimately maintaining our room offset of negative 100. So in this room right here, our supply and exhaust our general supply and general exhaust have the full capability to offset what the fume hoods are doing, or the fume hood is doing, which means that we have a 100% diversity condition. So let's take a look at an example of diversity. So if we have the same room where we're still trying to maintain a negative 100 CFM offset, but our supply has a range, or our supply has the same range and our general exhaust has the same range, but now we have 3 fume hoods, where when all 3 fume hoods are closed, we have 300 CFM being exhausted, and when they're all open, we have 1800 CFM being exhausted. So with all of our fume hoods closed here, we have 300 CFM of total fume hood exhaust. Our general exhaust controls to 900 CFM to ensure that we maintain 1200 on the total exhaust, ultimately maintaining our room offset. So if we have a full lab now and 3 individuals go to each of the fume hoods and open them up, what we'll find is that our fume hood exhaust to control to the face velocity on each fume hood is going to increase to 1800 CFM. So each hood is going to control up to 600 CFM. Our general exhaust valve here, in an attempt to maintain our room offset, has fully closed. So we're only exhausting 90 CFM on our general exhaust valve, giving us a total exhaust of 1890 CFM. Now our supply valve in this case, trying to maintain the room offset, has increased to its maximum value of 1500, but it's not capable anymore of maintaining our 100 CFM offset. So our offset has increased to negative 390 CFM. So we've over pressurized the space. This would be a condition where diversity does exist. So because our supply system can't keep up with our exhaust, we have diversity. In this case, we would need to implement a system where we train the lab users that they can only have 2 fume hoods open at any given time. They should not be opening all 3 at the same time. So our last topic for today will be test methods for fume hoods. So fume hoods require field certification to ensure that they are performing accurately or adequately, and the following standards here, I'll discuss the proper test methods for these fume hoods. The first one that we'll talk about is ASHRAE 110. This is a very expansive test and is very commonly specified. It's also, as we go through the standards here, the different types of standards, we'll also find that ASHRAE 110 is either commonly referenced or used as a template by other standards. So ASHRAE 110, like I mentioned, is very expansive. We will focus today on the sections 6.1, 2, and 3. So we'll be discussing the face velocity measurement procedure, our VAV face velocity control test, and the VAV response test. So if we start with our face velocity measurement procedure, the first thing that we want to do is form an equally divided grid in grid spacings of no more than 1 square foot, where the largest side of the rectangle is not exceeding 13 inches. Once we've divided the hood opening up into that grid, we're going to take readings with the calibrated anemometer at the center of each of those grid rectangles. The last important thing here in this paragraph is that the sensing element of the anemometer shall be held in the plane of the hood sash. So taking this into account, if we have a fume hood that has a 40-inch width and our design height is 18 inches. According to the standard, what we'll do here is we'll divide this up into 8 individual grids or 8 individual rectangles with dimensions of 10 by 9 inches. The next thing that we'll do is we'll set up our hot wire or our anemometer to measure at each of the center locations of all of those grids. So we'll end up with 8 readings for each of those, or for the full face of the sash. That'll give us a great idea of what the average face velocity is across the entire face of the sash. The last important note here is that we want to measure in the plane of the sash. So what this means is that we want to be in the plane of where that sash hood opening is. If we start taking readings that are outside of the hood or inside the hood, we'll start to see a very drastic drop-off in what we measure versus how much face or how much velocity there is actually going through the face of the sash. The next thing that we'll consider here is, or the next test that we'll perform here is a VAV face velocity control test. So to do this, we'll be using what we just discussed in how to measure velocity, and we'll be measuring at 25% of the design hood opening. So our first test here, if we have a design height of 18 inches, would be at 25% of that, so 4.5 inches of the opening position of the sash. We'll take our readings at that position after we allow the system to stabilize. We'll then increase the sash to 50%, so 9 inches of opening height, and we'll again let the system stabilize, and we will take our readings again. The last measurement that we'll take is at that design hood opening, so at 18 inches. Again, we'll allow the system to stabilize and take our readings using the previously mentioned method. Now, the purpose of this test here is to understand that the VAV control system is able to control to 100 feet per minute at each of these different heights. The next test that we'll discuss is the VAV response test. This test is designed to understand how quickly we react to changes in the sash height. So to start the test, what we'll do is close all of the sashes and record the reading of the laboratory hood monitor. We'll then begin recording at a rate of 1 reading per second using a data logger. And after 30 seconds of taking readings at the close position, we'll open the sash from the close to the design opening at about a rate of 1.5 feet per second. So it's important to not move the sash too fast as it will, we will see a lag in the system then. After 60 seconds at the opening position, we'll want to close the sash at that same rate of 1.5 feet per second. After we've completed one of those cycles, we'll repeat that whole cycle 3 times. So, as I mentioned, what we're looking for with this test is how quickly our system responds. The first thing that we're looking for is what's called the VAV speed of response. And this is the time measured from the first movement of the sash for the VAV system to restore the airflow to 90% of the average steady state value. So in this case, in our mock example here, we're measuring from the time where our sash starts moving, so where this red line starts increasing, to where we reach 90% of our airflow required for 100 feet per minute on the exhaust valve. So that is defined as our speed of response in ASHRAE 110. The second thing that we're measuring and recording as a part of that test is the VAV time to steady state. So this one is defined as the time from the first sash movement to when the system regains and controls to within 90 and 110% of the average steady state value. So this one is not just our initial response, but it's the time from when the sash starts moving to when we stabilize our control. The last thing that we'll discuss with ASHRAE 110 is the equipment that should be used for measuring face velocity. So face velocity measurements should be taken with a recently calibrated thermal anemometer that meets our ASHRAE standard of 111. This device should have the capability of measuring a range of 30 to 400 feet per minute with an accuracy of 3% of reading or 3 feet per minute. So moving on to ANSI Z9.5. As I mentioned at the beginning of this test methods for Fume Hood section, some standards do just reference ASHRAE 110. ASHRAE, or ANSI Z9.5, is one of those. So the commissioning and routine testing of a fume hood shall refer to ASHRAE 110. One of the differences with ANSI Z9.5 is how we define the VAV response time. So ANSI states here that the VAV response shall be sufficient to increase or decrease flow within 90% of the target flow or face velocity in a manner that does not increase potential for escape, and that we're defining this here as being recommended within less than 3 seconds after the completion of the sash movement. So the big thing here is just how they define that speed of response. Here we can see that it's defined as the completion of the sash movement rather than the start of the sash movement. So in most cases, less than 3 seconds will be acceptable, according to ANSI. These next couple standards here we'll go through a little bit more quickly, as they do refer back to very similar test methods as ASHRAE 110, but I'll try to highlight some of the potential differences or criteria that they outline in these standards. So the CSA Xiii16.5 standard highlights that to measure airflow or measure the face velocity, we'll be dividing the grid into a 12 by 12 or into 12 by 12 inch squares, very similar to ASHRAE 110. We'll be using an anemometer here to measure at the center of each grid, recording 20 readings at a rate of 1 second per reading. Now, how we're going to report that is the face velocity shall be the average of the velocities recorded at all the grids used. And if that average falls outside the range specified prior to the test, then it should be noted on the report. So this is where, when understanding what's being used in the fume hoods, it's important to define ahead of time what the range of operation for the fume hood is. The maximum individual variance among all the readings should be plus or minus 20% of the average reading. And if we do fall outside any of those ranges, then we make a note on the report. So for measurement, it's very similar to ASHRAE 110 with those extra couple little notes. For the VAV response test, we have a very similar test method here as well, where we begin a cycle by moving to the closed position and leaving it closed for 30 seconds and allowing the airflow to stabilize. We then open the sash to the sash test position at a rate of 1.5 feet per second. We also measure and record the airflow for 60 seconds while at that opening position. After 60 seconds has elapsed, we close the sash and start the whole cycle again. So we repeat that cycle 2 times to make sure that we have a total of 3 tests. CSA defines their response time as the time required for the controller to adjust the VAV steady state back to the lower limit of the VAV steady state range. Now the steady state range here, again, needs to be something that's defined in advance, but it is the range of the variation in airflow velocity that's allowable relative to the VAV steady state velocity. And then our time to steady state here is defined as the time required by the VAV controller to adjust the VAV steady state velocity back into and then keep it in the VAV steady state range after the sash has been opened from a closed position. So if we look now after those definitions at some criteria, CSA lays out some response times and some time to steady state that they consider good and poor. So our response time, so from our initial time of the movement of the sash to when we complete 90% of our movement or enter that acceptable range, should be less than 5 seconds for a good response time. The time for us to stabilize and control within our steady state range should be less than 7 seconds to be considered good. In terms of airflow measure or face velocity measurement, CSA does call out specifically that velocity grids should not be used for face velocity measurement. We should be using a single point anemometer. The last standard that we'll discuss today is the NEB procedural standard for testing fume hood performance. And essentially, again, the layout for the grid or dividing up the sash is very similar to ASHRAE 110. We'll be using a square foot or no greater than 1 square foot with no dimension larger than 13 inches. And when we measure that face velocity, we'll be measuring at the center of each grid. We'll be measuring 20 samples at a rate of 1 per second, and we'll report the average of each grid location. One thing that I do want to note that NEB outlines here is that the total fume hood exhaust volume is not equal to the average airflow face velocity being captured through the sash opening. So additional air will enter through the hood under the airfoil and could also penetrate from the sides of the fume hood or any other leakage points. So when we're balancing fume hoods and balancing the airflow valves for those fume hoods, we want to be careful not to equate the airflow that we calculate going through the sash opening to how much airflow is going through the valve. There should be a test procedure called out for the face velocity, and if required, there should also be a test procedure called out for performing the balancing of the fume hood exhaust valve. When we take face velocity readings similar to ASHRAE 110, we'll be wanting to take the readings at the full open sash position. We'll want to reduce the sash position to 50% of the opening and let it stabilize before we take our readings. And then we'll also want to reduce to the 25% position and take our readings. The response time defined by NEB, or the response time testing, involves 3 cycles of opening and closing the sash at a rate of 1.5 feet per second. If we also look at the definition for the VAV speed of response and VAV time to steady state, We'll also see that they are very similar to ASHRAE 110 in that response time will be the time from the first movement of the sash to when we achieve 90% of the average steady state value. And the time to steady state would be to when we move the sash to when we restore and control between 90 and 110% of the average steady state value. So, to summarize all of the topics that we discussed today, we talked about the types of rooms that are included in the scope of ANSI Z9.5 and NFPA 45. And we also discussed the types of equipment that are included in the scope of ANSI Z9.5, ASHRAE 110, CSA Xiii16.5, and NEB. We also discussed the air changes per hour as described in ASHRAE Laboratory Design Guide, ANSI Z9.5, and NFPA 45, as well as the speed of response as defined in ANSI Z9.5. We discussed the air distribution recommendations provided by the ASHRAE Laboratory Design Guide, ANSI Z9.5, CSA Xiii16.5, and NFPA 45, and the room pressure guidelines that are outlined in ASHRAE Laboratory Design Guide and ANSI Z9.5. And finally, we discussed the fume hood diversity as described in ANSI Z9.5 and ASHRAE 110. And finally, the test methods for fume hoods in ASHRAE 110, ANSI Z9.5, and CSA Xiii16.5, and NEB. So with that, I'll pass it back to Nicole.
Hello, everyone. Thank you for all of your questions. We have quite a few, so we only have time to answer a couple. The first question is there a standard that dictates a minimum fume hood CFM when the sash is closed?
Yes, this is actually defined in another section of ANSI Z9.5 that we didn't talk about today or discuss today.
Thank you, Mike. Second question is there a testing requirement to measure the velocities near or flowing across the hood face?
Yes, there are in many of the standards guidelines for measuring the cross flow in front of the fume hood. Those do exist within most of the standards as well.
And finally, we've had several questions related to the slide deck. Following this webinar, you will receive an email that contains a link to the PDH quiz request, as well as a copy of the slides. So all unanswered questions from today's webinar will be answered by the presenter and will be sent out later on. If you have any questions concerning the webinar or your PDH credit, please email us at marketing@antechcontrols.com or applications@antechcontrols.com. Please visit our website at www.antechcontrols.com for a list of all upcoming webinar events and a list of all of our upcoming engineer training. This concludes today's presentation. Thank you for attending. We hope that you will join us again for our next webinar.